Hello everyone. I'm going to talk today about searching for solar siblings, looking for the sun's sister stars that were born in the same cluster as the sun. And we've got an illustration on the title screen here of a few of the sun-like stars and the nearest stars to the sun, and a few of the planets there to scale. So Sol, that's the sun here. Some of these other stars are a little bit smaller than the sun in the case of Alpha Centauri B, a little bit larger in the case of Alpha Centauri A. And we're going to take a look at how we can work out if any of these stars are the sister stars of the sun, or if they just happen to be nearby, and consider what we can find out. So most stars are born in star clusters. They are produced out of a nebula, and it tends to produce a range of sizes and colors of stars. There's a star cluster shown here with a number of hot, bright blue stars. And then if you look in the background, you'll see there's some slightly fainter white stars that are the next level down in terms of mass and power output. And then you go fainter down to the yellow and orange, and even down to the little red dwarf stars, which are very, very hard to see indeed in the photograph. So that's the typical sort of mixture of stars. You'll get a lot of small ones and a few large ones, because it's easier to make enough mass gather together to make a small star than it is to pack it together to make a real monster. And this is a sort of what we're contending with. The sun's sisters could be any of these, and could have come from a cluster out there in the galaxy somewhere. So what should we look for? Should we look for stars that are still nearby the sun, or stars that have a similar orbit to the sun around the galaxy? Perhaps we should look for ones that are similar composition in terms of the mixture of elements. Maybe we should look for similar types of stars, or in particular, similar ages. That would be good, because if they were born together, they'd all have the same age. Well, the first thing is we could look at nearby ones. This is sensible because nearby ones are much easier to study, and we'd be able to learn more about them more easily. And the way we determine if something is nearby is really, first of all, we look to see if the position against the apparently unmoving, very distant stars is changing, the so-called proper motion. As the star zips across our line of sight compared to the background, the position will appear to change, and that's a clue immediately that it's a nearby star. And that process is illustrated in the diagram on the left. And on the right, we have the method we use for measuring the distance to nearby stars, which is to look to see how the apparent position changes over the course of 6 months as the Earth moves around the sun, changing the line of sight to the nearby stars versus the very distant ones that don't appear to move at all. And we can measure the angle and do a little bit of trigonometry and work out the distance away that the star must be. Now, in terms of looking for stars that are nearby, or that as regards them being sisters of the sun, the problem is that we are orbiting around the Milky Way galaxy at a distance of 27,000 light years from the center. And so it takes 230 million years to do a complete lap of the galaxy. But whilst that sounds like a very long time, the sun was born 4,500 million years ago and has completed 16 full orbits since it was born. And this is rather means that any companions, if they had just a slightly different velocity, or were moving in a slightly different direction, they will have become separated from us as the giant stirring has occurred. It's very much like stirring a cup of tea. You put the spoon in and whisk it round 16 times, then the milk will be thoroughly mixed up and distributed into the cup. And that's what has happened, really. The sun's sisters, they must be out there, but they're stirred very effectively into the rest of the stars of the galaxy by the fact that we've been round so many times. Were we looking for much younger associations of stars, if the sun was much younger, then it might be possible. And there's a good example of this called the Ursa Major co-moving group. Ursa Major, or the Plough, or the Big Dipper, shown in the photograph there, is actually a collection of nearby stars. Most of the bright stars there are part of a group that were formed together just 300 million years ago. So they've only done one lap of the galaxy and haven't been completely scattered and stirred yet. And there's probably 14 main stars and maybe as many as 50 total that make up this group, that all seem to be going in the same direction at the same speed, hence the name co-moving group. And they're scattered over a region about 30 light years across, about 80 light years away from us. And that all points back to them having an origin in a small cluster, something like 300 million years ago. And gradually they're spreading out, and give it long enough, you won't be able to tell that they were once all together, because they will have been stirred into the galaxy, as has the case with the sun, because it's 15 times older. Now, another thing you could use as an indicator, and this is a very good indicator of the age of a star in many ways, is to look to see what chemical composition it has. The slide here is entitled metals, because astronomers refer to all elements heavier than helium as metals. This, I think, greatly annoys chemists, because there are many non-metals that are actually heavier than helium. Things like carbon and oxygen, for example, not even rare. But nevertheless, that's the term that is sometimes used for the heavier elements from element 3, lithium, onwards. But the point is that the chemical composition of a star, if you can measure it, gives you a clue as to its evolutionary history, and in particular, how long ago it formed. And the reason for that is that the interstellar medium of gas and dust, which collapses eventually to form stars, began life as 75% hydrogen and 24% helium, with just a trace of the heavier elements, and a known trace as well. But as time goes on, massive stars form, evolve, and die as supernovae and scatter their contents all across the cosmos, polluting the material with the heavy elements that they have manufactured. And so gradually the composition of the universe getting dirtier and dirtier, with more and more metals present. Now, what this shows here on the graph is that you can measure the vertical axis as the composition of stars in terms of the ratio of heavy elements to light elements, and then look at the age, and the young stars, intermediate stars, and old stars are clearly separable into these three groups here that we've coloured blue, green, and red. I mean, you could have put the dividing line anywhere you liked, but the point is that the composition gradually gets increasingly altered as the time goes on. And this is because younger stars have been formed out of more polluted interstellar medium, where there's been more time for the interstellar medium to accumulate more and more of the metals. So if we look at the composition of the sun, we can use that and try and find stars that have the same composition, because they indicates they were potentially formed at the same time, or out of the same cloud of material even. Now, you might look at this graph and say, oh, look, there's quite a big scatter for the older stars. This is because, in fact, when you look at the older stars in red, and also true for the green grouping got two peaks in it, dropping down, and the red has got several rows in it. This is because the Milky Way consists of the merger of several smaller galaxies, and the oldest stars may well have come from those original galaxies and been on slightly different evolutionary tracks. And so we get different subpopulations that we have to worry about. Now, what about looking at stars and considering the type of star and whether we should worry about whether it's a sibling of the sun or not? Well, this chart shows different classes of stars, from red dwarfs at the bottom, orange dwarfs, yellow dwarfs like the sun, yellowy white stars, bluey white stars, and then the bluest of the blue at the top there. And the horizontal axis is showing the lifetime, with each column, each step being 10 times the life of the previous column. So the biggest supergiant blue stars, they blow up very rapidly as a supernova in just 1 million years. The next class down lasts 10 times as long, so they'll last 10 million years. For the white stars, it's more like 100 million years, and then they blow up. The bluey white ones, it's perhaps 1 billion years, and then they're gone, and they die less spectacular deaths as planetary nebulae rather than supernovae, but nevertheless scatter their material into the cosmos. Stars like the sun, 10 times again, so 10 billion years, and then again planetary nebulae and scattering the material. And so on for orange stars, 10 times longer again, and red stars, 10 times longer even than that. But these ages have never been achieved because the universe is only 13 billion years old, so no orange or red star has yet been born and come to the end of its life, because they live so long that there just hasn't been time for that to happen yet. Now, the point of this is that the largest stars burn bright and die young, and so there's no point in considering them to be siblings of the sun, because any big bright blue or white star just simply cannot be old enough. It would never have been possible for it to have been in existence as long as the sun has, because they will have run out of fuel. And indeed, most of the yellowy white ones, the more massive of that middle class star, those probably wouldn't. They only last 1 billion years, and the sun's already 4.5 to 5 billion years old. So most of the yellow white stars can be ruled out as well. Really, the only ones we need to consider are the sun-like stars, the ones that are very slightly more massive than that, and the lighter orange and red ones, because they're the only ones that can have been around since the birth of the sun. So perhaps with all that borne in mind, we should have a look at the nearby sun-like stars. Sun-like stars, because anything brighter is going to be too young, and nearby because they're the easiest ones to study. So let's start in our backyard with Alpha Centauri. Alpha Centauri is a triple star system. The two components are called Rigel Kentauris, or Alpha Centauri A, Tollyman, Alpha Centauri B, and Proxima Centauri, because it's the nearest star to the sun. And A, or Rigel Kentauris, is a little bit bigger than our sun, Tollyman a little bit smaller and an orange coloured star, but very, very similar in lifetimes and so on. Now, at the moment, these two orbit each other quite closely. and we have yet to discover any planets that orbit around either Alpha Centauri A or B. But we have found that there are 2 and probably 3 planets orbiting Proxima Centauri. And it wouldn't surprise me if we eventually discover that there are planets around the other 2 as well. Another nearby star is Tau Ceti. Again, in the illustration here, we have the sun on the left and Tau Ceti, for comparison, on the right. A little bit smaller than the sun, a little bit cooler, so 80% the mass, 428 degrees cooler, at 5344 Kelvin. And that reduction in temperature and reduction in size is enough to actually reduce its overall power output to half that of the sun. But it's got a confirmed family of planets, and 2 of them are potentially in the habitable zone. So very, very interesting indeed. And it's 25% older than the sun. So any evolutionary processes going on there will have had more time to do interesting things. Also in our backyard, cosmically speaking, is Epsilon Eridani. This is again a little bit smaller than the sun, smaller even than Tau Ceti, and has a temperature just over 5,000 degrees. So it's an orange star, a K-type star, not a G-type star, but a very late K. And this one's very young. We can age it looking at the behavior of the chemicals in its outer layers, and we figure it's less than 1 billion years old. Now, it probably has a Jupiter-sized planet and perhaps even more other smaller planets still looking into that. And it's going to be a prime target for the James Webb Space Telescope to have a look at. Also, going a little bit further away from the sun, but looking at sun-like stars, we find another G-type, very similar to the sun, just 103% of the mass, 101% of the radius, and 104% of the power output. So I think you'd agree that's very sun-like indeed, is 18 Scorpii, and the distance and brightness are shown at the top of the screen there. Now, if we try to work out what's going on, we can look at how these things behave, what happens to the temperature of them and so forth. And it's showing us that this is still quite a young star, so 2.9 billion years old, not yet settled down into its most stable phase. So it's not quite onto the main sequence yet. But again, quite a good candidate for a sun-like star. Now, here's a sort of timeline of stars like the sun. We're here 4.6 billion years since forming out of the nebula. 18 Scorpio, much younger, 2.9, nearer the beginning of its life. And so still increasing in brightness as well. Interestingly, they failed to detect any sort of dust disk around it, looking for an infrared heat signature of a dust disk, but they have discovered a planet that orbits in just under 7 years, going around the sun, around 18 Scorpii, which again makes it a very sun-like system. One way in which it's not like the sun, though, is rather curious in that it has 3 times as much of element number 3, lithium, as we do. And that's peculiar because the sort of characteristics of these stars are such that you perhaps might not expect this. So we can find that lithium tends to be destroyed if it gets dragged into this stellar core. And main sequence stars where fusion of hydrogen is going on in the core usually end up stirring enough of the lithium to destroy it into the core, and so they tend to be very low in lithium. Um, However, some sun-like stars have a host of, or are the host of a set of planets, and these can have lower lithium abundances, provided abundances don't lead to them being harvested in a destructive way. So using machines to rip out all the vines, for example, and then get the bananas off them would not be allowed. Now, some couple of stars that have got numbers rather than catalogue names are of interest. This one here, 186302. It's just a little bit less massive than the Sun, and it's been suggested that this one might, in fact, have been born from the same cluster. We're not sure. The temperature profile is interesting, and the orbital parameters of it have been studied in a paper from 2019, and it looks like it might have been thrown out of the cluster, as I said, but it's quite early for it to be being kicked out, and there are still a lot of hot blue stars around, so we're not quite sure about this one. Perhaps more certain as a solar sibling is this one, HD 162286. This is out there in the constellation of Hercules, 115% the mass of our sun, but about the same size, and appears from all our measurements as 4.5 billion years old, so the same as the sun, and just 103% of the metal content of the sun, so hardly any difference at all. That makes it probably the best candidate for this solar sibling status. In orbit around it, there are no hot Jupiters. That's good. But the terrestrial planets that they have may well be in the habitable zone. There's one here in a Mars-like orbit, which could potentially be habitable. So why do we care about the sun's siblings at all? Is it just a sort of academic interest to see how typical the sun is of the stars that it was born with? Well, really, it's because of this hypothesis. Early in the history of the solar system, any solar siblings with their associated planets would have been relatively nearby the sun, perhaps even still in the same early star cluster. Now we know that there are a lot of collisions that occur between planets during the planet forming process, and that planets occasionally get kicked out of a solar system, and it's therefore possible that the seeds of life could go with them, either as part of a planet or a meteor or something that's been carved off of a planet. And life is very, very resilient in terms of the surviving the rigors of outer space. So it's just possible that the seeds of life, or life itself, might have been shared between systems, between the planets that belong to the sister suns. So it would be very interesting to look at these sun-like stars that seem to have the same age and come from the same original cluster. And if we find non-zero ones of those, then perhaps we could very simply just be looking for life that might have hopped from one star system to another. So thanks very much for listening. I hope that was enjoyable. Do click the subscribe button and look at some of our other talks that we have on here.